right, good morning, everybody. Go ahead and get started. So, I think we're going to go back a little bit because I talked about on Monday some inverse demand versus normal demand, and then neutral. Even though we kind of touched the asymmetric part, I want to come back to this because this is actually a really important reaction doing the invert, like an inverse electron demand, where you put a donor on your dienophile and a electron withdrawing group on your diene. And I'm going to show you a couple of applications. So this is one application by Tang and his group, and they kind of combine with Hoke, who is a computational chemist. And so what they did was they took this start material that you see here. This is kind of the retrosynthesis part. So this is the product that they were aiming for, elysicolin H, or they call it 8-epi elysicolin H, right? So this proton right here is the difference between those two compounds. So elysicolin H, 8S, has this on a wedge, if I'm not mistaken, and then the 8-epi has it on a dash. So this is a really cool experiment. For one, it's an inverse electron demand experiment, but then for two, right, it's an application to a really clever synthesis of this natural product, which is an antifungal from this starting material tetraene, and you can see right here that this diene is set up for uh, inverse demand because you have an electron withdrawing group on your diene, uh, and you and so what they were looking for is the stereo selectivity as well as what they call peri-selectivity. Right, the peri-selectivity part is this going to be inverse demand and do a 4+2, or is it going to be normal demand and just do a 4+2, but with a different diene? And so that actually made a difference, and you can control the product distribution by the solvent. Right down here, if you do it in water, you got your inverse demand product versus your normal demand product, and a ratio of 2 to 3. So there's a competition. If you do it in toluene, then this product is formed in 3 to 1. It's still competition, but that's a little bit of an increase in the product distribution for the product that you want, which is this product right here, right, with the inverse demand. Um, and what they found out was that they could catalyze this by using a particular enzyme, and I'll show you on the next slide. Um, and with the enzyme, the reaction is carried out at a rate that's 300,000 times faster than just doing the reaction without the catalyst, doing it in water or in toluene. All right, so this is the enzyme, the ICCD. And what they found out was that this enzyme belongs to a class of enzymes called pericyclases, which catalyze pericyclic reactions like uh, cycloaddition, like 3,3 sigmatropic rearrangements, things like that. So this ICCD enzyme, they isolated from uh, this particular Aspergillus nodulans A1145. So they went in and found out that this cassette of 5 genes was a part of this bacteria. So they're able to isolate it and then isolate the ICCD enzyme itself. Because what they found out was that with the ICCD, this was the enzyme that actually catalyzed the inverse demand reaction. The other enzymes did not. They did a really clever experiment where they, did the reaction with all the other enzymes. Then they did them with each one separately, and then they added in the ICCD enzyme, and they found out that uh, this particular enzyme right here does inverse electron demand, Diels-Alder. And then another enzyme within that cassette, that 5 enzyme cassette, was the ICCE enzyme. And that's the enzyme that actually did the epimerization, right? So you take this proton and basically remove it and then put it back, but you put it back on the opposite side. That's what epimerizing means, to take a chiral center and either destroy it or reverse it. So that's what the term epimerization means. And what this is what they found out. Like when they took um, with ICCE, they got product one, which is here, right? And then this is just this was product two, which is the inverse demand here, but they wanted this product, and so they had to. That's how they determined that this enzyme was the catalyst for this epimerization, right? Um, and so another really neat thing they did was to start with this start material and look at the reactivity without ICCD and with it. So you can see over time, right, 4 is the start material, and they monitor this by HPLC. So 4 is the start material here. And then over time, 5 minutes, you start to see some of 2 grow in. 2 is this, it's the inverse demand. And then 5 is the normal demand, right? So you can see here, 2 is starting to grow in. And then over time, you see a little bit of 5, and the same thing here, and the same thing. So 2 is favored, right? But if you look at the conditions for toluene, you have a 76 to 24 ratio of 2 to 5. But over here is 99 to 1 using that uh, enzyme catalyst. So this was cool, and it was all based around the fact that the inverse demand Diels-Alder would give you the proper product, right? Where the cyclization happened with inverse demand, so you get different regiochemistry, which led to the product that they were looking for, which is this 8-epi uh, ilicicolin. All right, so another application of that inverse demand is here, and this is actually taking uh, biomolecules like DNA and then outfitting them with these tetrazole rings, right? So this is just a basic scheme right here. So what they did was took the norbornene side chain or side group, functional group, and they added it to one of the side chains of a biomolecule like DNA or some other polypeptide. So they did these cycloadditions reactions to label these biomolecules so they could track like what's happening with the polypeptides and other reactions. Um, so this was also an inverse demand Diels-Alder, right? And you get these derivatizations that are irreversible. So now you got these molecules labeled and you can track them, use them for other purposes, and you know what's happening with that particular section of the polypeptide. And this is how they characterized it, right? So they have the norbornene modified polypeptide, which is right here, and they track this by PCR. Then when you do a single Diels-Alder, you can see here, and then double Diels-Alder, you can see here, and then the triple Diels-Alder, where you have like more than one of those norbornene side chains that's reacting, and it's through inverse demand Diels-Alder. So the inverse demand Diels-Alder is pretty important from the perspective of it can be applied to a lot of different situations, and the scope of the reaction is broad enough to where you can even include it in biomolecules as well as total synthesis of molecules that have biological significance. So I wanted to go back and touch that because I didn't want to leave that hanging. But you can do the Diels-Alder either with regular or normal electron demand or inverse electron demand. Um, so we already talked about this part. We talked about this on yesterday. Uh, we talked about the Danishevsky, not yesterday, Monday. We talked about the Danishevsky's dying. So let's talk about some the hetero Diels-Alder. And so the hetero Diels-Alder reaction is when you use for your dienophile some other um, functional group other than alkene, right? So in this case, your hetero Diels-Alder reaction is happening between the Danishevsky's diene here, and this is some work that was done by Jacobson in 1998, published in the Journal of Organic Chemistry. But you have your diene, which is the Danishevsky's diene, and then your dienophile. And one of the things that the hetero-Diels-Alder reaction takes advantage of is, if you remember back here, when we first talked about the Danishevsky's diene, we were talking about how the Z group, whatever the Z group is, it needed to be amenable to beta elimination. And so a lot of your hetero-Diels-Alder products have that beta elimination product happening, right? So that's why you see this and not the 6-member ring with the substituents still on there, right? All you get is this. So this carbonyl is coming from here. It's the deprotection of the TMS group, and then you eliminate off the methoxy group, right? So that's what that product. That's how you get this product right here. Um, it's normal electron demand, and if you look at this particular work by Jacobson, this is this is his catalyst that he developed, this chromium salin complex. So this ligand here, that's what's called a salin ligand, and it's substituted with a lot of different substituents, right? You can put a chlorine, you can put tert-butyl, you can put a Z, you can all these different functional groups you can swap X and Y out with, right? So you can see here X can be a chlorine, it can be an azide, fluorine, or BF4. And then Y you can swap out with different alkyl groups, or even an alkoxy group. And what the neat thing about this is that it was really kind of like one of the first reactions that where this was done asymmetrically. Over here is just a list, just the scope of the reaction. You can use benzaldehyde. You can use an alkyl chain. It doesn't matter, alkyl, aliphatic, aromatic, alpha beta unsubstituted. It doesn't matter. You still get good yields, right? Your yields ranging from 65% all the way to 92%. And then you get good enantiomer selectivities, right? No, these ones that are in parentheses, those were taken after recrystallization. So some of these products were, if they were oils or liquids, right? You can purify that, and these are your enantiomer selectivities. But if the product is a solid, you can actually recrystallize it. And so notice here, you went from 76% EE to 99% EE. And the same here, 83% EE to 99% EE. This was after recrystallization. So obviously, there are some differences in the physical properties of the two enantiomers. So it's almost like doing a resolution, even though it's not quite a resolution. Uh, and then right here, you can see the same thing happen with the different catalysts. It says 6A and 6B. So 6A has BF4 as a counter ion, and then the Y groups are tert-butyls, and then 6B is BF4, but the Y groups are methoxy groups. But you don't see any real diminution in the yield, uh, and you don't really see like a drop off in enantiomer selectivity. You see a little bit of increase actually with the tert-butyl group, but you would expect that because it's a more bulky substituent, so it's going to make that bias around that catalyst, and the bias in the transition state is going to increase that a little bit. All right. So that's the one of the first asymmetric hetero-Diels-Alder reactions. You can also do what's called an aza-Diels-Alder, which I think is on another slide. But you can also do what's called an aza-Diels-Alder reaction, where your dienophile is an imine. But we'll talk about that in a minute. So here's another. This was done by Dean, and this particular reaction was done, if I'm not mistaken, is solvent free. Yeah. So this reaction is done neat. So you just mix your diene with your aldehyde, and the R groups again range from aromatic to aliphatic to alpha beta unsubstituted, alpha beta unsaturated. and you can use either catalyst A or B. And if you notice, the differences in the catalyst uh, are here, right? With the cyclohexane ring. This should be if you notice, both of this side is uh, saturated, and then over here, this is the same ligand that's up here, right? So they just vary the catalyst in that way by varying the ligand, and it does have an effect, somewhat of an electronic effect on it, but it's not a huge effect, right? So R can be aromatic, it can be substituted aromatics with electron donating groups, electron withdrawing groups. The range of your catalyst. Again, when we talked about catalysis, this is important. 0.05 to 0.1%, which is huge because that means if you need to scale this reaction up, you can. And the catalyst loading with a catalyst loading this low, 0.05, that's excellent. And your EEs range with catalyst A from 75 to 95% EE for this product, right? And this enantiomer. And then with catalyst B, which is here, the same catalyst loading, but the percent EE ranges from 97 to 99%. Both give high yields, and again, this is done neat, which is important. Uh, Doing a reaction neat, meaning doing it without solvent, is important in the sense that if you want to scale this up, or if you want to do it, if you want to let it have some industrial applications, then a lack of solvent is actually a good thing. It's because that's one less step. Normally when you do a reaction uh, in organic, if you're doing a reaction, you're doing it in some solvent like dichloromethane or methanol or THF or water or something. There's always going to be a step at the end of the reaction after you work it up, separate everything, where you're going to have to get rid of the solvent. And in this particular case, you don't have to do that because there's no solvent present. All right. So the AZA Diels-Alder I have shown here. This was also done by Ding and co-workers, uh, published in Organic Letters in 2002. So this particular reaction is an acid-free reaction, right? So you need an acid to deprotect that um, the TMS group right here, right? Normally, if you're using Danishevsky's diene, you need an acid to deprotect that. But this is acid-free aromatic aldehydes, really broad scope with that. You can even use some alpha beta unsaturated aldehydes. Um, and you can also do this in acetonitrile, but I think the methanol was chosen for one reason, and that's because you don't have an acid, but you do have a proton source if you use methanol. Acetonitrile, you won't have that proton source. Um, and again, this is your uh, heterodeals product. You can see the N group right here is incorporated in that six-member ring. That's an important um, aspect of the reaction because now you're making heterocyclic rings with stereochemistry, which is a good thing, especially when you think about application to some larger uh, motif where you're doing a natural product synthesis or something to that effect. Um, if you look at the yields, this is a very high yielding reaction from 63% all the way up to greater than 99% yield. And the scope is good, right? Electron donors, electronic acceptors uh, attached to that aromatic ring, and it doesn't matter. You would now this is kind of counterintuitive. This result right here, where you have a uh, 4-nitrobenzene, a paranitrobenzene here, and the yield drops, right? You would expect putting an electron withdrawing group on your aromatic ring that it would somewhat activate your dienophile, but that's actually the lowest yielding. Um, that's the lowest yielding result that they had. So, and also what they did was did a three-component variant of this because sometimes if you have imines and they have alkyl groups on them, then they can be a little unstable. And so what they did was they generated the imine in situ, right? So they took the aldehyde and the amine, which is the way you make shifts bases, react those together, and then syringe in the Danishevsky's diene on the back end. And these are very high yielding reactions as well, right? And that's just to, again, this is just a modification to account for the fact that sometimes if you use aliphatic, it means they're not that stable. Um, so this is the mechanism, and what they're proposing is not uh, a traditional 4+2 pathway, right? If that was the case, then you just push electrons here, here, and then move that down and get this six-member ring, right? But that's not what they observed. They did not see this at all um, for this reaction. What they did see was a manic reaction, right? And a manic reaction is the imine derivative of an aldol addition, right? So you can see right here, this is an enol, this is a solid enol ether, kind of like a Mukayama aldol reaction. Um, but instead of reacting this with an aldehyde, like you would do in an aldol, you actually react it with an imine, right? And so this enol is going to attack the imine and give you uh, this alpha beta unsaturated amino ketone, which is here, right? And then when you treat this with water or some proton source, it actually cyclizes. So I have the over here. You can see how this happens. So you attack the imine like so, because here you have your TMS group, which is a latent enolate. So if I think about this in terms of the enolate, it looks like this, right? So I'm using the electrons here to make my CO pi bond at the same time I'm attacking with the carbon-carbon pi bond here. So I make this new carbon-carbon bond, and then if I have this in a environment where this can be protonated, right? I can attack here with the nitrogen to form this intermediate, and then if I protonate that methoxy group, I can just lose it through beta elimination, and that's how I get to my product. So they don't see the traditional Diels-Alder pathway here, right? And this is uncatalyzed. It's just this is just reacting these two together at room temperature in methanol. All right. So what probably happens in this case, so it's plausible that doing this in methanol actually frees up the oxygen to get here. So it actually pops that TMS group off, and then you get here, and that's why it follows the manic pathway as opposed to uh, just going through a traditional 4+2 cycle addition. All right. Here's another example of the aza Diels-Alder. This one is an anti-selective, where they took this ME here, right? This is my catalyst. And this is similar, if you think back to some chemistry we talked about with the aldol addition. This is kind of in the vein of like a Scott Denmark type catalyst. This was done by Leighton in 2010. This is like a Denmark type catalyst where you use silicon as your organizing element for your transition state. So it's kind of like a Lewis. It's almost as if the silicon is like a Lewis acid, and it kind of organizes everything. And you can see that that's what's proposed down here. And so what happens in this particular case is you actually get competition between a 3+2, which is where we get our 5-member ring from here, and that's what's shown here, right? You get the silicon is here, right? So nitrogen can put a pair of electrons to here, and then you also have this nitrogen here becoming as a imine or imine type, right? Using that pair of electrons, and then you put a pair of electrons on the oxygen. So then you can chelate to the silicon in that way, right? And then this actually does intramolecularly, you do this 4+2 here, right? After the addition. But the I'm sorry, the 3+2 to get you to here. And that's a 1-to-1 ratio. of this to this. But then if you look at the path B, that gives you your traditional 4+2 cycloaddition. So after what they looked at here is just the competition, and they studied the ratios using different functional groups here, right? So with paranitro benzene right here, you get a 1 to 1.5 ratio of 3+2 to 4+2. You get with the paramethoxy 1.8 to 1.1. Orthomethoxy 1 to 1.8. So it's starting to favor the 4+2. So what they did was they made R here a tert butyl group, and with R they got 69% of this, all right, exclusively, with no competition from the 3+2. So this is a traditional like Diels-Alder reaction product, and the 3+2 is no longer competitive when R is a bulky tert butyl group, right? So here, these are the optimized conditions. They do this in dichloromethane, room temperature, overnight, 1.5 equivalents of your catalyst. And so let me take that back. Let me not say catalyst. It's a promoter. It's not a catalyst. If it was a catalyst, then it would be less than one. The ratio would be 1 to 0.01 or zero point 0.1 or zero point 0.5 or something like that. But since you're using this in a stoichiometric amount, then it's not catalytic. So let me apologize for misspeaking there, because we've talked about that before when we talked about organo-catalyzed reactions, which is this is an organo-promoted Diels-Alder reaction, right? So here we take our diene, 1.5 equivalents of the promoter, the silicon promoter, and this is the product, 91% yield, 85% EE, right? And this is what the promoter looks like. So this is where your chirality is coming from. And again, if you're going to use that like a Lewis acid, then it's got to be able to chelate your nitrogen groups, have to be able to bind to it in order for that reaction to happen, right? And this is just a scope of reaction in uh, toluene or in chloroform. Either one of those solvents were used, and then we have where the R group here is a methyl. It can be a chain, right? It can be an ether, which is right here. Uh, it, all of these different functional groups, all these different substituents here, uh, and you don't see any real diminution in the yield, with the exception of when it's done in toluene and R as a phenyl group, and then when it's done in chloroform, and you got this parabromo benzene as your substituent. But look at the enantioselectivities. Selectivities. This is really good. 98%. I'm assuming that this is minus 81 because you get the other enantiomer. Because normally the EE is not reported as a negative number. So I'm assuming they did that to say that you get the opposite enantiomer here. Um, yeah, but you got 85%, 87, 90%. So that's pretty remarkable. And so as a extension of the scope, they wanted to use this particular reaction to generate these tricyclic, heterocyclic ring systems, right? So you can see right here, if you're starting with this as your backbone and you do a 4+2, you're going to put another 6-member ring right here, right? So 2E is this, right, where there's a tert butyl group here on the amine here, and then your promoter, 1.5 equivalents of that, and then either toluene as the solvent or dichloromethane. And with that, you can see right here, you get 62% yield and 83% EE. in toluene, or 66% yield and 86% EE in dichloromethane. And this is the product, right? And you can see you set now two chiral centers using that promoter. And this hasn't been observed before here. I have these particular examples highlighted. Uh, what they did was, in this case, they started with 2E, and this was the diene that was used. Again, reacting that with 2E dichloromethane at room temperature at 24 hours. So you see here that A for 12A, X is hydrogen, and then for 12B is chlorine right here, right? So this is regular demand, 97% EE, 95% EE. Whether X is hydrogen, you get 97%, and then whereas chlorine, you get 95%. Uh, so with this, they see regular demand, but when they change up the ester moiety over here, it flips to inverse demand. Even though, let me go back to 2E. Uh, 2E is right here, right, where this is a isopropoxy group. And then right here, they change it to an ethoxy group on the ester, and it changes the electron demand. It goes from being regular demand to inverse demand, right, where this is a methoxy group. So that observation had never been seen up to this point. I think this was published in 2010. That observation hadn't been seen up to this point, where you can change the regiochemistry from regular demand or normal demand to inverse demand just by changing up the substituent here. That hadn't been seen, and this doesn't proceed through a manic pathway. This actually does go through a traditional 4+2 mechanism. It doesn't go through a manic followed by some type of addition then elimination. It actually goes through a 4+2 mechanism. All right. So the Diels-Alder again is used for a lot of different applications, but this particular application stood out to me because of the application to the synthesis of a natural product. Right. So this cytosporalite, this was the original structure proposed by Chi, but uh, a second structure was proposed where this ring here was closed. This six-membered ring right here is actually closed up. That's what you see right here, right? So this oxygen is actually here, and then this OO bond is not there, right? That's a carboxylic acid. That's what you see over here. So uh, Takao and co-workers actually used a Diels-Alder strategy to make this uh, six-membered ring to close it up, as well as make the right structure. Right, this is the proposed structure, but this is actually the right structure. They actually proved this structure by some really elaborate NMR experiments to prove it. So that structure was revised, and Takao and co-workers actually proved it a second time. And then of course, when you have a method, you want to target. So this was the target for their method, and they were working on Diels-Alder reactions to begin with, right? So Cytosporalite A, this was their retrosynthetic strategy. They had already been working on something like similar to this, where they started with this particular alkyne and used that as one of the star materials to eventually get to this ring system right here, which is uh, you can see here has multiple stereo centers and multiple rings, right? Very, very important structure in the grand scheme of natural product synthesis, because a lot of your natural products, like your some of your alkaloids and then some of your other natural products like Taxol and things like that, they have these multi-cyclic systems in them, with multiple chiral centers set as well, right? All right. So this they knew that they could get from this Fuchs control A, and then the second piece. which is how they envision breaking this ring up into those two pieces. The second piece right here, they knew that they could get that from this particular product, CJ 12373, right? So with those two pieces, they were going to put this ring system together. So this is the synthesis. So this is how they got from here, which they started with this, right? So Foods Control, they started with A, they started with that, and reacted that. We can just go through this to see how they got to here, right? So they reacted this with, they did a, converted this into a mesylate. Let me move this thing out of the way. Right, converted this alcohol into a mesylate, and then using, again, you can see these protecting groups, MOM and MPM, right? They use DDQ and a phosphate buffer to remove that MPM protecting group, right? And then from there, they just did a reduction, palladium catalyzed reduction to get rid of the mesylate. So now you are here. And then a dibarrel reduction of the ester here gives you this alcohol. And then they just treated that with base, DBU, and did an elimination to get you here and pop that ring open as well. Um, and then another sodium borohydride, cerium catalyzed sodium borohydride reduction got you from here to here, where they just reduced off that aldehyde down to the alcohol. So that's one part of their uh, synthetic strategy. That's one piece. And then for the other piece, right, they started with this substituted aromatic ring, treated it with butyllithium, and then did an epoxide opening. So they converted this into the aerolithium, which is a great nucleophile. Then they treated that with the epoxide and popped it open. So they got this alcohol right here, and then hydrogenated off the benzyl protecting groups to get here. What they found out was that once they got to, um, well, let me not jump the gun. So they did a esterification here. So they added the carbon dioxide and potassium bicarbonate to put that carbonyl group here, the ester. It actually ended up being a carboxylic acid. And then they treated with allobromide to make the aloe ester that you see here. And then converted this alcohol into this acetal, right, with ethanol. And what they noticed was that when they got here, they had a different strategy, but they couldn't pull off like the ethoxy group. They weren't able to deprotect that acetal. So they scrapped that strategy, and then they went with this strategy where they used this palladium pyrrolidine and then add in ammonium chloride. And when in doing that, they were able to free up uh, this alcohol right here, right? So they want to deprotect the acetal, not pop it open, right? So this right here, you can see kind of right here, you can see that this is kind of like an enol, even though it's within an aromatic ring. At some point, that ring would re-aromatize if this double bond gets used like an enol. But you can see the enol right here, and then you can also see right here that this is kind of set up for uh, as to be used as either a dienophile or a diene. Right. So if we look over here, right, they took three, which is this star material that they made here, treated it with benzyl chloride, and then treated it with TES chloride and DMAP. So both of those are protecting strategies. And that's why earlier when we talked about protecting groups, that's a like a vital, really vital strategy for doing synthesis. Right. You have to be able to manipulate those protecting groups to protect your functional groups that you don't want to react with other things, right? So you can see right here, now you have this is set up to react here, right? So they reacted this with 22, which is this, or with 4, which is this. And I think this 22 was the product that they got to when they weren't able to deprotect this, right? And that led them to the synthesis of 4, which I just showed you. So 22 was the other product uh, that came from a series of steps, and it ended up with this uh, ethoxy group not being able to be deprotected. So that's why they ended up with 4. So this get and again, you can see now right here. So this and 3 reacting together. This is your Diels-Alder right here. So you can see this is your diene. So your hetero part is not with the dienophile in this case, but the diene. So this is the cyclization right here to close up that ring system. And that's how you get to product 33, which is right here, right? With that ring system closed up in the proper fashion and with the right stereochemistry, right? So once they got to here and protected the alcohols, the next step was to actually do the Diels-Alder, the hetero Diels-Alder reaction, right? And again, this is your diene right here, and you can see it right here. If I you had to rearrange those, but you can see right here, um, here, right, and then that diene, the hetero Diels-Alder happens here, right? And it's reface approach. So it's showing you again for 32, it's actually approaching from the bottom face of that. And that's how the stereochemistry is set. All those pre-existing stereo centers kind of uh, make that reaction happen the way it does, right? And then so it's coming from the bottom face, and then you get 33, which is here. So then after they got 33, you can see 29% of recovered 32 and then 35% for 33. So it didn't go to completion, but they were able to isolate this, right? And then the next step, they just did a diabel reduction um, here to take off the uh, benzyloxy group, and then treated with HF and pyridine to take off the TES group, right? And so that got them to this final product where this ring is closed up. This ring is still intact, right? Even though it was the ethanol group was here, that ring is now still intact. And this is the Cytosporalite A, which was the initial target. Well, all of this happened because they saw the potential for a Diels-Alder reaction here with this star material that they had previously synthesized. So I think actually out of time. Uh, I think when we come back, we're going to talk about the photochemical Diels-Alder, which shouldn't be possible, and it is not possible under thermal conditions. It's not possible based on the Woodward-Hoffman rules. The 4+2 is not possible uh, in a for photochemical 4+2. You can't get the proper orbital overlap, but there's a way to get to a 4+2 product using a different type of substrate, and we're gonna talk about that on Friday. All right. Any questions about anything? I know this was a lot, but you can see here they did like the NOE experiment to look for the right coupling and make sure that the right stereochemistry is in place. So and they actually calculated that J value for the methyl group here, coupling with this proton down here, HA, and you can see that the coupling was 9.5 hertz. So all of these other methods had to be employed, right? They had to employ NMR, and they had to employ mass spec. They employed a lot of different methods in order to get to this final product. And then what you'll see is that a lot of times you're not going to do a total synthesis without having to do like some of these advanced spectroscopic methods, right? You're going to have to do NOSI and COSI and NOE experiments and all of these types of experiments to prove these structures. It's not as simple as just taking an NMR of it and then knowing, matching up the protons. It's you have to do a lot more than that. Um, so yeah, so we're gonna stop here. We'll pick this up on Friday.
All righty.
All right, appreciate it, and I'll see y'all then. And I'll upload this PowerPoint.